The following video is on derivatives, tangents, velocities, and other rates of change. You probably learned about average velocity in your pre-calculus class. You learned that average velocity is given by the change in distance over the change in time, or the total distance divided by the total time. But what if we want to find the speed that a car is going at any given moment? How does the speedometer know how fast to tell you that you're going? That's called instantaneous velocity. And in order to do this, your car measures the distance that you've traveled over a very short period of time. In other words, we're taking the change in distance over the change in time, or the average velocity, as the change in time goes to zero. We then just want to find the average velocity over smaller and smaller intervals of time. So, how do we find the instantaneous velocity? Here we see a graph of a function that relates the time in seconds along the x-axis to the meters traveled along the y-axis. So we have distance versus time. The average velocity over the time interval from 2 to 6 is, remember, given by the change in the distance over the change in time, which, if we look at that, we end up with the slope of the line connecting those two dots. Remember, the slope is the change in the y values over the change in the x values. The average velocity from 2 to 4 then would be the slope of the green line. Once again, it's the slope of the line because we're looking at the change in the y values over the change in the x values. So similarly, we can think of the instantaneous velocity at x equals 2 to be the slope of a line. The only difference is that we're looking at the slope of the line as the time interval around x equals 2 is infinitely small. Now let's define tangent lines. Consider the function f of x given below, and we want to find the slope of this curve at x equals 1. If we zoom in to the curve at x equals 1, notice that the curve almost looks like a straight line. Anytime we have a straight line, we know how to find the slope of it. We just find the change in y over the change in x. So if we zoom in enough and the graph looks like a straight line, we call this line the tangent line of f at x equals 1. I've shown you the tangent line in this graph in purple. The tangent line is the graph that's approximately the same as the line when we zoom in to the graph at a point. So how do we find the slope of the tangent line? Well, remember, the slope of a line is the change in y over the change in x, but we want the change in x to be getting very close to 0. So the slope of the tangent line will be the limit as delta x goes to 0 of delta y over delta x. Remember from our average velocity example a minute ago, we were looking at velocities over time intervals from things such as 2 to 6. We call those lines secant lines. The slope of the secant line is just the average velocity. The slope of the secant line at x equals 2 in this example is f of 2 plus h minus f of 2 over 2 plus h minus 2. Notice that the 2's in the denominator cancel, and we're left with the change in the x values really is just h. The tangent line at x equals 2 then is the limit as h goes to 0 of f of 2 plus h minus f of 2 over 2 plus h minus 2. That's the change in y over the change in x, or the slope of the average velocity, but taken as the time interval goes to 0. Once again, the 2's in the denominator cancel, And we're left with the slope of the tangent line. Notice that the change in the y values is really f of 2 plus h minus f of 2, and the change in the x values is still h. The slope of the tangent line to f at x equals c is called the derivative of f at c. Another way to see this, once again we've got the graph of our average velocity from 2 to 6. The slope of the tangent line at x equals 2 can be found by the limit as x goes to 2 of f of x minus f of 2 over x minus 2. Notice that we're taking the limit as x goes to 2. So once again, we're looking at the slope of the c-cat line as the 2 points get closer and closer together. The derivative of f at x equals c is the limit as h goes to 0 of f of c plus h minus f of c all over h, or the limit as x goes to c of f of x minus f of c over x minus c. And in both cases we have to say, provided these limits exist. We write f prime of c to represent the slope of the tangent line to f of x at x equals c. F prime of c is our notation for the derivative of f at x equals c. The derivative tells us the slope of the tangent line, which we saw earlier is the instantaneous rate of change of a function at a point. That's why it tells us the instantaneous velocity. Let's do an example. A ball is dropped from a roof that is 100 meters high. Its height at any given time is given by s of t equals negative 10 t squared plus 100, where t is measured in seconds. How fast is the ball moving at t equals 1 second? In order to find this, we want the instantaneous velocity at t equals 1. So we need to find s prime of 1. Using the limit definition, we have the limit as h goes to 0 of s of 1 plus h minus s of 1 over h. We plug in 1 plus h into my function s of t, and then we subtract what happens when I plug in 1 into my function s of t. Notice that the 100 cancels with the other 100 because we have to distribute the negative sign all the way through. So now I'm left with the limit as h goes to 0 of negative 10 minus 20h minus 10h squared, so I've FOILed out the 1 plus h squared and distributed negative 10 all the way through, plus 10 because that's remaining in the second term of the numerator. And all of this is over h. The 10's cancel from the numerator, and now notice that we have an h in every term of the numerator. So I can factor an h out of every term, and I end up with h times negative 20 minus 10h all over h. Since the h is being multiplied through every term of the numerator, we can cancel the h from the top and the bottom. And now, doing direct substitution, we get negative 20 minus 10 times 0, or negative 20. Notice that instantaneous velocity should be measured in meters per second, so our final answer will be negative 20 meters per second. You might notice that the answer here is negative. The answer is negative because the distance between the ball and the ground is actually decreasing, or in other words, the ball is moving downwards. In general, s of t is given by 1/2 gt squared plus v naught t plus s naught, where g is the acceleration due to gravity, v naught is the speed or the velocity at time 0, and s naught is the height or position at time 0. On Earth, gravity is approximately negative 9.8 meters per second squared, or negative 32 feet per second squared. G is negative if the object is moving toward the Earth or toward the ground, whatever planet we might be on. If an object is simply dropped, the velocity at time 0 is actually 0 meters per second. The only time it will have a positive velocity is if it's actually hurled down. The instantaneous velocity at time c is given by s prime of c equals the limit as h goes to 0 of s of c plus h minus s of c all over h. Remember, that's the instantaneous velocity, which is given by the derivative of the position function.